take a deeper dive into different left-right behavior, one of the reasons in which a limit could fail to exist. Well, up until this point, when we found a limit, we always looked on both sides of a. And the reason why is that informal definition said that f of x had to approach a unique value L as x approaches a from either side. But now we're just going to look on the left side or the right side individually, and this is called a one-sided limit. Over here in red, limit from the left, x as x approaches a from values that are less than a, that is from the left side of a, f of x is going to approach L. So let's look at the notation for that. You can see that the only difference here is that there's this little superscript that looks like a negative power. It's as if a is raised to the negative, and that's it. The limit as x approaches a from the left of f of x is equal to L. And we don't care about the right-hand side, just on the left side of it. Over here in blue, the limit from the right as x approaches a from values that are greater than a, that is from the right side of a, f of x approaches L. And so you can see that the notation on this one has a superscript which looks like a plus sign. X approaches a from the right. As x approaches a from the right, the limit of f of x is equal to L. Let's take a look at some graphs to go along with each one of these. Over here on the left-hand side, we have the limit as x approaches a from the left of f of x is equal to L. So this means I only look on the left side of a, numbers that are smaller than a, and our function is approaching this L value, whatever that happens to be, and we could care less what's happening on the right-hand side. Okay, likewise, the limit as x approaches a from the right of f of x is equal to L. So this time I approach a from the right side, numbers that are bigger than a, and our graph is still approaching this L value, whatever it happens to be, and we could care less what's happening over here on the left. So let's look at example 5, where we're finding each one of these one-sided limits. And we are using that function that we started this thing with, absolute value of x over x, which we said did not exist due to differing left-right behavior. And we will see that play out in this particular example. So number 1 is asking us the limit as x approaches 0 only from the left of absolute value of x over x. So I examine numbers that are smaller than 0, just the left side here, and I can see our function is approaching -1. Okay, on number 2, the limit as x approaches 0 from the right, numbers that are bigger than 0. So that's this right branch that's over here, and we can see that this absolute value of x over x is approaching +1. Each of these individual one-sided limits exist. This one's equal to -1, and this one's equal to +1. But since these are not the same exact number, we would say that the limit as x approaches 0, and that implies both sides of the absolute value of x over x, does not exist due to differing left-right behavior, which brings us to the existence of a limit. Let f be a function, and let a and L be real numbers. Before I continue, this whole thing about real numbers, calculus, as we're going to learn it, is 100% real numbers. All those imaginary numbers you talked about last year and the year before that, I'm not going to say you disregard them or forget about them. It's not part of this course. If you ever wanted to know about the calculus of complex numbers, it's a course all by itself. And if you take that course, you're pretty much getting yourself a math degree. Anyway, we're going to say the limit of f of x as x approaches a is L if and only if biconditional statement. Both of these things are true. The limit as x approaches a from the left of f of x is equal to L, and the limit as x approaches a from the right of f of x is equal to L. Both the left side and the right side approach the same unique number. Okay, so let's take a look at example 6, in which we have a piecewise function, this graph g of x, and we want to use it to evaluate these various limits here. We'll scroll down. This one's in pink. Okay, so I'll choose the little pink color. Part A, the limit as x approaches 2 from the left of g of x. So let me locate 2 here and I only want to know the left side of this, it doesn't matter that there's an open circle here. The graph still seems to be approaching this function value of 3. So I'm going to say that this one's equal to 3. Part B, the limit as x approaches 2 from the right of g of x. So this time just numbers that are bigger than 2. And this time it looks like it is approaching the number 1. Each of those one-sided limits exist. However, when I look at C, the limit as x approaches 2, that implies both sides, the left and the right of g of x, we're going to say that that does not exist. So we just write D and E, and I probably follow it up with a reason, and I'm going to say something like different left-right behavior, right? Now, I'm going to maybe extend this just a little bit and ask a question. Well, what is g of 2? What's the actual function value here? Well, when I look at the graph, look at x equals 2, notice that there isn't anything. There's open circles on both of these branches of the graph, and so this is undefined. Now, even though it's undefined, it doesn't necessarily have anything to do with the fact that the limit did not exist. The reason why the limit did not exist at 2 is because the left and the right side did not exist. I'm sorry, the left and the right side were different numbers. Okay, let's look at D. The limit as x approaches 5 from the left. So this time we're looking at x equals 5. Numbers that are smaller than 5 on the left-hand side, it looks like that we're approaching 2. So we'll say that that value is 2. And on E, the limit as x approaches 5 from the right side, numbers that are bigger than 5 this time, still is approaching 2. Doesn't matter that there's an open circle there. Our graph is approaching the number 2. Okay, and then on F, the limit as x approaches 5, there's no plus or minus, that implies both sides, of g of x, it's approaching 2 from both sides, as we can see here. Therefore, we can conclude that this limit is equal to 2. So the limit does exist because the left and the right side both approach the same unique value. All right, let me again follow this up with the function value, g of 5. G of 5, when I look at the graph, is actually this googly eye that fell down, and it's at 1. So notice that g of 5, the function value, is different from the limit. And it doesn't matter. It didn't matter that there was an open circle here at that particular value. That didn't affect whether or not the limit exists. And the function value itself does not affect necessarily the value of the limit. We're going to learn, though, that when these two things are the same, the function value and the value of the limit at that particular point, if that is true, then the function is continuous at that point. And that's kind of the goal of this whole entire unit.